to another mathematics lesson. We're investigating probability. Now, in the previous lesson, we wanted to ask the question, can mathematics help us predict the future? And we saw some tools that we could use that may be useful. Might not predict exactly the future, so don't get too excited. In this case, we're going to focus on situations when there are more than one thing could be predicted. So for example, will it rain as well as reach a temperature of above 25 degrees on a particular day? Those are two unrelated events, and we could put a whole lot of things together. Now, obviously, what you'd like to know is what would happen if we had 7 events, because that's the kind of number that will win you the lotto. But we're not going to go there today, I don't think. So let's have a look at what we're going to do and ask some questions about calculating the probability when we have more than one event taking place, either at the same time or shortly after. So, investigating the probability of 2 events, have you ever thought about, is it possible to find the chance of 2 events or more occurring, 2 or more events occurring? Well, if we look at our tools of probability that we've had, we recognize we know how to do some of these things. We recognize we know how to do the calculation of theoretical probability. We also recognize the idea of a sample space, and we're going to introduce and spend some time on this idea of a Venn diagram before we get to dealing with 2 events. So let's just go over some key ideas. So the first thing that I want to do is I want to talk to you about what is the sample space. Now, remember that when we were speaking about calculating probability, we said we wanted to consider all the possibilities that there were for a particular event or for a particular scenario or experiment. When we did the relative frequency calculation, we counted all the trials, the number of times you tossed or rolled a dice or tossed a coin. That will give you the total number of possibilities that will come out. So when we're rolling a dice, we recognize for one dice, there are only 6 possible outcomes. Either it can be 1, 2, 3, 4, 5, or 6. Now, what we recognized is all those values form the sample space. And out of those, we're going to select the ones that are the ones that we would like to have. Do you remember what we call the ones that we'd like to have? Of course, those are the favorable events, the ones that we are going to be the winners for. And so let's just make sure we've got the notation right. So remember, the sample space is recorded as a number S. The number of events in a sample is N, and then in brackets S. And here's an important relationship. The probability of something taking place in the sample space is the number in the sample space divided by the number in the sample space, and that's equal to 1, which tells us that whenever we've got an experiment and we don't make any restrictions, the maximum probability is 1. We know for certain it's going to happen. So whenever you see a probability of 1, you know you can be 100% sure. And that's a very important relationship. We're going to use it a little later. Right, let's have a look at the next term. Representing the sample space, we do it in a space like this, where we say, let's use a rectangle, and we're going to call it S. Now, within that sample space, we can put in certain other sets, smaller components. We refer to these as shapes, as Venn diagrams. They can be sets that limit a certain condition that we're wanting to investigate or explore. So a Venn diagram goes into the sample space and focuses on our favorable outcomes, or the things that we would like to happen. Let's have a look at the notation. So we notate a Venn diagram with an X, and you can say that the number of things in a Venn diagram would be nx. The probability of X occurring, this is the theoretical probability, is the number of x divided by the number in the sample space. And our graphic representation of the sample space and x is simply the rectangle that represents all the numbers, all the possibilities, and x here represents those that we are most interested in. So that would be the Venn diagram for x. Now, if we were going to go a little bit further, it would make sense for us to do some examples to explore this idea of the sample space and Venn diagrams. And so I want to look at a little situation. Instead of pulling numbers out or socks out of a bag like I did in a previous lesson, I'm wanting to look at the letters of the alphabet. And we're going to divide them into different groups. Let's have a look at the criteria we're going to need. So we're going to let the sample space be the first 10 letters of the alphabet. And we're going to let set X be the vowels taken out of that first 10 letter set. So if we were to draw that, we recognize that we've got the sample space there with the 10 letters of the alphabet, and I think all of them are shown. And there you can see that X is only focused on the vowels out of those 10 letters, namely A, I, E. We don't go to the others. They're not in the sample set. So don't think you need to include O and U. No, they're not in the sample set. The sample set was only for the first 10 letters. And X, the Venn diagram that we've shown there, is only showing you 3 of the letters in the first 10, the 3 vowels that we've got. Right, let's move on. We've got that. We could say to ourselves, what is the probability of selecting an element from X? Well, that's not too difficult. We know that the number of elements in X is equal to 3. We also know that the number in the sample space is 10. And so if we were to calculate the probability, we'd recognize it's these two numbers divided by each other. And if we look at it graphically, we're going to take those ones and we're going to say, there we go, we've got 10 in the sample space, we've got 3 letters, and we take 3 divided by 10, which gives us a probability of 0.3. Now, that was really quite easy. Remember, this is the theoretical probability. And so we've been able to do many of these examples, but what's different in this case is that there is more than one favorable outcome. We could have A, E, or I as an outcome here, not just a black sock or a white sock. There's more than one possibility. But remember what I said, we wanted to investigate when we have 2 sets. So let's define a second set. Our second set will be as different, will also be part of the Venn diagram, sample space. We're going to draw a Venn diagram. The first one was X. This second one we're going to represent as Y. And it's going to be the first 3 consonants of the alphabet. Do you remember what the consonants are? Those things that aren't vowels. So the consonants, the first 3 consonants would be B, C, and D. Let's see if I've got it right in my diagram on the Venn diagram. So there's the Venn diagram, and there we go. We've got B, C, and D. They belong to the set that we are going to call Y. And you can see that there is nothing in common between these two. They're quite different. And if we were to play a game, and we could say you could win if you draw either an element from set X or from set Y, well, then you've got a number of different options. Let's just make sure that we've got the idea clear about theoretical probability, though. I want to calculate the theoretical probability of selecting an element from set Y. So remember, we've got 3 things in the set, and we're going to calculate that. Notice that the sample space is still 10. We've got 3 in Y, and we recognize that it's going to be a third. So if we were to be very clear about that, we'd recognize we can calculate the probability of set X, set Y, and we can then come to some sort of conclusion about them. I want you to think about this. What would the probability be of calculating both of them? Maybe that's something to think about. I'm going to give you a few minutes to think about it. Take a short break, and we'll be back to explore that a little bit further. Welcome back from your break. I hope you're ready to do some more investigations about probability. Now, in our first little segment that we were looking at this first lesson, we wanted to make sure that we understood certain terms like sample space and calculating theoretical probability. Now's the opportunity for us to look a little bit closer at how we deal with two sets. So let's go and have a look at these. So two events can be represented in different sets, and we used a notation which we refer to as a Venn diagram. So the Venn diagram helps us to deal with events, whether they're two or more, and we're going to be looking a little closer at specifically two events. And the first thing that I want to deal with is this idea of a union. Now, what does union mean to you? Union means joining together. Well, in maths, it's a little bit more complicated in terms of probability. And I want you to get this idea very carefully. So I'm going to go very slowly to make sure that you've got it. Remember in our example that we were busy dealing with, we have calculated independently the probability of X, and we've calculated the probability of Y. When we talk about the union of X and Y, we're talking about something that contains all the elements of X and all the elements of Y. So please make sure it's the two together. But we don't use the word and, just like I went over the top and said and. It can be either in A or in B. It's very important that you get the meaning of this correct. Union means or. And we kind of make that mistake. We think it must be and, but it's actually or. So let's just make sure that we've got it right in terms of our definitions. So the union of two sets, it's a new set that contains all of the elements that are in at least one of the two sets. So it must have all the elements of X, but it needs to make sure that we've got at least all the elements of X. It can also have the elements of Y, but some of the elements of X could be in Y, and that's why we use the notation X or Y. Please notice that the word union has got this symbol that looks like a U. So it's up and down like this. Now, in our example, let's just make sure that we've got X and Y, those two Venn diagrams. What would the union of X and Y look like? Well, have a look and see. There we've got the 10 letters of the alphabet, the first 10 letters of the alphabet, and we've extracted the vowels over here for the set X, and we've extracted the first three consonants for Y. Now, what I want you to see is that the union of these two will look like that. It contains everything that was in X and everything that was in Y. And so we've written it as X union Y. Now, if we're going to do some probability calculations, then the question is, what is the probability of selecting an element that belongs to the union of X and Y? Make sure that you can see this very clearly. And so I want you to take a very careful look at the diagram that represents the sample space and the union within it. Here we go. So if you look here you will see that we have 3 elements that were part of X, and we've got 3 elements that were part of Y. So in total, we've got 6 elements that belong to the union of X, Y. So remember this, the English word that we need to be saying is we're wanting to calculate the probability of an element being in X or in Y. And so when we do the calculation, we're going to say that as we go. So that the number in the sample space we recognize in total is 10. But the number in the union is only 6. It's either 3 in X or 3 in Y. Together, they make a total of 6. So the probability of X union Y or X or Y is 6 divided by 10, and that gives us a number of 0.6. Now, guys, that's quite interesting, but it's also quite strange, because if we wanted to say, we've worked out earlier what was the probability of X, and then separately we worked out the probability of Y, and now we've worked out the probability of X union Y or X or Y. I want to ask you, is there a relationship between these? Can we somehow do a relationship or a calculation to help us deal with this idea of union? Well, fortunately for you, we are on track. And that's the very question that we're going to ask. What is the relationship between the probability of the union of 2 sets and the probability of the individual sets? So let's have a look at it. If we look at the space, the sample space, you'll recognize that what I've got written down here is the probability of X on its own. And we worked out that the probability of X on its own was 3 divided by 10, which gave us a probability of 0.3. And the probability of Y on its own was also 0.3. Now, what do you think the probability of the union would be? We worked it out. Do you remember? We said the probability of the union was 0.6. And we've drawn the purple box around them just to show that the elements are in either X or in Y. And if they're in either X or in Y, then you could be the winner if those were the rules of the game. So what's the relationship? Well, I hope you can see that if we take 0.3 plus 0.3, we're going to get 0.6. So from this example, we can have this general statement. The general statement is that if we've got a union, which is saying what's the probability of X or Y taking place, then we can take the probability of X plus the probability of Y. But guys, that only works for this example that we've done. We need to make sure and ask the question, will it work all the time? Are there some situations when this rule or identity doesn't hold true? Well, remember, in our case that we've done here, we've taken 2 very particular sets or 2 very particular events, set X and set Y. And remember, I said to you, there was nothing the same in each of them. They had no common element. And therefore, this identity holds true when that's the case. Now, we need to define that and put some more terminology into that idea. So let's have a look. We're going to make sure that we have that definition for you in our next little segment of this lesson. Up till now, I want you to think about what's happening. If we have these sets that don't have anything in common, then the rule is we can take the probability of the first one plus the probability of the second one, and that will give us the probability of either the first one or the second one together, the union. Guys, I hope this is making sense, and I hope you follow very carefully, because this is very important for you. In our calculations of probability and of two sets, make sure you understand what is going on, and make sure you understand this identity of the calculation of probability of X union Y. We'll come back and explore it a little bit further after the short break. Welcome back to our lesson on probability. Now, I'm sure that you are enjoying the idea of being able to predict the future using mathematics. Probability helps you understand what are the chances of certain events taking place. And it doesn't just have to be one event. It can be more than one event. Now, in this lesson, we're exploring the idea of two different events taking place. And so let's get into the idea of the two events. And what are the nature of these two events? Are they related? Do they have some common elements in them, or don't they? Well, that's exactly what we want to explore, because maybe the rules are different for different types of events that are taking place. So let's have a look. We're dealing with two events, and we recognize that these two events can either be thought about as both of them together, in which case the winner might be found if they have an outcome in one of them or the other. So union is always referred to in terms of the word or. Whereas what we want to look at is the idea of intersection. We've already seen that in terms of intersection, some two events have no intersection. And we're going to explain what this word then means. The idea of something being mutually exclusive. So right from the beginning, let's talk about intersection of two sets. So if we have an intersection, well, that means that they overlap in some way. It also means that there's an element must be in set A and in set B if it's part of the intersection. It just can't be in A on its own. It can't be B on its own. It has to be in A and B if it belongs to the intersection. And so that's a very important thing, because the intersection is smaller than the union. Please remember that. We kind of get that mixed up in our heads, and we can make a mistake by not recognizing that union means the bigger thing, and we're saying that it is in A or B, where the criteria for intersection means it must be in A and B. So it's smaller, it's common. But of course, there's a situation where the intersection could have no common elements, like the examples that we were dealing with in the previous segment. So let's just have a look in our definitions, how we define intersection in a little bit more detail. So the intersection is a new set that contains all of the elements that are in both sets. So it's not just in one, but they must be in both. You can't be in the intersection if you're not in both. We write the idea of intersection not as a U, but an upside down U. So it's that funny symbol. If we draw it like that. And remember, intersection is referenced as and. Now, how can we remember this? Well, a friend of mine was telling me one of the ways that he remembers this, if you have two roads that are running at 90 degrees to each other, then the intersection is the part of the road that belongs to both of them. So if you've got a road running from north to south, and you've got a road running from east to west, that part that belongs to both roads, that's the intersection. And it's smaller than the union of those roads. The union of those roads would be either to be on road that is running from east to west or on the road that is running from north to south. Okay, so please be very clear about your language here and build up a mental picture so that you are very clear about what intersection and union mean. Because lots of formula and examples and exercises will relate to your understanding of these two important words. Let's move on. So we're going back to our example of our 10 letters. And remember, that's the first 10 letters of the alphabet. And we recognize that is in the sample space. We recognize X has got 3 letters in it, and Y has got 3 letters in it. There is no common element. There is no intersection between X and Y. We would have to say that the number of elements in the intersection of X and Y is going to be 0. Okay? The number of elements in the intersection is 0. There is no overlap in this space. And so, because there's no overlap, there's no element, there's no crossing over, it's like two roads that don't ever meet. They could be running parallel to each other. They're going to be nothing in common with each other. And so we say that the intersection is a null set. It's an empty set. Okay, very important for that. They are separate. And this is where we want to get to in defining a very important idea of two sets. And it's the idea of something being mutually exclusive. Wow, that's a difficult word or phrase to get out. Mutually means something in common. Exclusive means that they are set apart. So they are different but set apart. So the idea here is that there is no intersection. So when we define mutually exclusive, it simply means events that cannot occur at the same time. Very, very important. Even at a high level on studies on probability, you would be asked to identify, is an event mutually exclusive or not? And it's not that difficult to recognize. If these events do not have anything in common, then they are mutually exclusive. So they can't take place at the same time. So for example, you can't put a sock on your foot at the same time as putting a shoe on the foot on that same foot. It can't happen at the same time. You can't take a dice and roll it and get a 6 and a 3 at the same time. Rolling a 6 and rolling a 3 would be mutually exclusive events. They cannot take place for one die at the same time. So please make sure you've got this very clear in your head. Now, we often need to test if something is mutually exclusive. And so we're going to do a little exercise or activity that helps us understand what that idea of, for mutually exclusive, the union of two sets is. So have a look at the data, and I want to remind you that they're asking you, or look at the data first of all. We're saying that the probability of R is going to be 0,4. The probability of T is going to be 0,2. And they ask us, in terms of these two sets that are mutually exclusive, they're written as mutually exclusive events, they're representing events, they're sets, Venn diagrams, and we want to be able to say, what is the probability of those two together? If it's mutually exclusive, remember we said the probability when it's mutually exclusive, we're going to recognize it's the probability of R union T, and we're going to say then that's equal to the probability of R plus the probability of T. Now, in this case, we recognize the probability of R is 0,4, and the probability of T is 0,2. We can add those two together to get us a probability of 0,6. Now, please remember that that law or that identity applies for mutually exclusive events. When there is no intersection, the probability of R or T taking place is 0,6. Very good. Let's move on and have a look at another example of the same application. And here we're going to ask the question is, does this identity hold true for events or sets that are not mutually exclusive? I want you to think about that. Do you really think that that will work or not? I want you to reflect on it. And I'm not going to answer it in this lesson, but you'll have to wait for our next lesson to do that. But in the meantime, let's have a look at another problem. And this problem says to us the following things. The following sets, are the following sets mutually exclusive? We know if they are mutually exclusive, then we can take the probability of each of them, add them to each other, and we would find the probability of the union. So let's make sure that we've got this clear. So for mutually exclusive sets, we can say, let's take the probability of M happening plus the probability of N happening, and we can say that's 0,7 plus 0,2. And look what we get. We get an answer of 0,9. And can you see that this is not equal to the probability of M or N? So it breaks apart. It doesn't look like it's following the identity. Well, you might scratch your head and say, have I made a mistake? No, you haven't made a mistake. The reason that these two do not add up, they are not equal, is because M and N are not mutually exclusive. And there we go. Guys, if you can remember this one fact, that what mutually exclusive means and how to determine it, I promise you, you will win at your probability investigations. We're going to have a look at what happens when there are elements in the intersection. But that we will leave for another time. We will think about whether that same identity can be applied. But before we go, let's have a look at a brief summary. So, what have we done so far in our investigations of probability? Yes, we've looked at Venn diagrams. We've recognized we can have a sample space with all the elements, and we can recognize that we can have a sample space with elements that belong to different sets. These sets don't have a common element in them, and we would recognize that these ones, as I've drawn them, are mutually exclusive. There is nothing in the intersection. On the other hand, I could have two sets, and I'm not going to call them the same. I'm going to call them P and Q, and in this case, let me just make this one a bit bigger. That one is Q, and you recognize there's an intersection. There are common elements. These are not mutually exclusive. So, recognize now, when we talk about union and intersection, we have a very clear definition of those two events. Make sure that you've got it. Union means we're always going to say the objects or the elements must be in the one or the other. So when we are calculating union, we're looking in either of them. Where we're looking at intersection, we're saying this is the smaller one, the intersection is going to be the and. Okay, so it has to be in both, common to both. It's in the intersection. Very good. Now remember, when we calculate the probability of the union, we have said the probability of the union is going to be the probability of A union B is equal to the probability of A plus the probability of B if the sets do not have an intersection. That is only true if we are dealing with mutually exclusive events. So, guys, I hope this is very clear. I know we've gone through a lot of different new terms and different terminologies, but please revise this and make sure you can apply your identities, your probability identities, for calculating probabilities when you've got two sets that you're looking for the union and they are mutually exclusive. That's been the main focus of what we're dealing, and I'm going to wish you all the best as you continue investigating more about probability.